we're going to go over a few concepts in calculus, starting with the fundamental theorem of calculus. Okay, let's take a function small f of x, and let's call the integral of f of x with respect to x capital F of x plus c. That's capital F. So that's the result of the integration. All right. If we're looking for this integral here, the integral of f of x dx between a and b, okay, a and b are called limits. A is the lower limit, b is the upper limit. So the result of this integral here is just capital F calculated at b minus capital F calculated at a. Capital F is known. That's just the integral. Okay. When you integrate from a to b, when you have limits, that's called a definite integral. This is called an indefinite integral, and this is a definite integral. And we don't need to add the constant c because it cancels. So no need for c, it cancels. We're going to show that in this example. For example, suppose you're calculating the integral of x squared dx between 3 and 6. What's this integral going to be? It's going to be a number. What's that number going to be? Okay. Well, first, the integral of x squared dx is x to the power 2 plus 1 over 2 plus 1, which is x cubed over 3 plus c. So we need to calculate it at 6, calculate it at 3, and subtract them. So calculate it at the upper limit, at the lower limit, and then subtract them. And here's the calculation. Calculate the integral at 6. So you have the integral was x cubed over 3 plus c. So that's 6 cubed over 3 plus c, which is 216 over 3 plus c, and that ends up being 72 plus c. Calculate it for x equal 3. So x cubed over 3 plus c is 3 cubed over 3 plus c, which is 27 over 3 plus c, and that's 9 plus c. Subtract those two. 72 plus c minus parentheses 9 plus c ends up 72 plus c minus 9 minus c. The c cancels, and the answer is 63. So the answer is 63. We could have done it directly using the theorem and without involving the constant c, because it always cancels. Let's do another example. Let's calculate the integral of 4x cubed minus 12x dx between 2 and 4. And the answer is going to be f of 4 minus f of 2. This time we're not going to involve the constant c. So here's the integral. You're integrating 4x cubed. That will be 4 times x to the 4th over 4 minus 12. The integral of x is x squared over 2 between 2 and 4. Simplify these. The 4's will cancel. 12 over 2 is 6, so that gives us x to the 4th minus 6x squared between 2 and 4. Calculate all of this at x equals 4, so it will be 4 to the 4th minus 6 times 4 squared, minus, calculate all of this at x equals 2. 2 to the 4th minus 6 times 2 squared. Calculate all of this, and it ends up being 168. Let's do another example. This example, the integral between 0 and 2 pi of 2 plus cosine x dx. The integral of 2 is just 2x. The integral of cosine x is sine x. Put brackets between 0 and 2 pi. Now we're going to evaluate all of this at x equals 2 pi. So it'll be 2 times 2 pi plus sine 2 pi. Minus, evaluate all of this at x equals 0. So it'll be 2 times 0 plus sine of 0. Okay, whether it's plus or minus doesn't matter because sine 0 is 0. 2 times 2 pi is 4 pi. Sine 2 pi is 0, 0, 0. So the answer is 4 pi. Example 204. You're integrating from 0 to pi over 4 secant squared x minus cosine x dx. So first you integrate. Secant squared gives you tangent. Minus cosine, that gives you minus sine. From 0 to pi over 4. So calculate all of this at pi over 4. So it'll be tangent pi over 4 minus sine pi over 4. Minus all of this at x equals 0. Okay, tangent pi over 4 is 1 minus square root of 2 over 2 minus 0 plus or minus 0, doesn't matter, and that's the answer. The average value of a function on an interval AB is equal to the integral from a to b of f of x dx divided by the interval itself, 1 divided by b minus a. So it's 1 over b minus a times this. Or you can write it as the integral divided by b minus a. Next, whenever you're integrating from a to b, any function, you can break it up. It's equal to the integral from a to c plus the integral from c to b. If it's easier to break up to allow you to do the integration, or for whatever purpose, you can break it up. The integral from a to a of any function with respect to x is equal to 0. Because it's equal to f of a minus f of a. Upper limit, lower limit. All of these are true provided that the function f is integrable and continuous. We're now going to go over the second fundamental theorem of calculus. The second fundamental theorem of calculus states that the derivative with respect to x of any integral of f of t with respect to t from a to x is always equal to f of x. We're going to show this by integration using the long way, then differentiation. Okay. So let's do example 205. d dx of all of this. So first let's calculate this integral here. The integral of sine t dt from pi over 3 to x. By the way, this letter t, you can use the letter u, z, any letter. The long way, integrate, then differentiate. So let us integrate this. The integral of sine is minus cosine between the limits pi over 3 and x. So it'll be minus cosine x minus negative cosine pi over 3. So it'll be minus cosine x, minus times minus is plus cos 3. Or you could write it as minus cosine x plus a half. Then take the derivative of it. The derivative of the result, the derivative with respect to x of negative cosine x plus a half is negative. The derivative of cosine x is negative sine x. The derivative of a half is 0. These two minuses cancel, and that gives you sine x. Okay. That's the long way. The short way is to use this theorem, the second fundamental theorem of calculus, which says this. The derivative is just f of x. So you replace whatever letters you have here, t or u or whatever, by x. Here's the short way. The derivative with respect to x of this integral here is just sine x. And that's what we got. So let us apply the theorem to a few examples. 206. You're looking for the derivative with respect to x of this integral here. So the theorem tells us it'll be square root of x cubed plus 1 because you're replacing this t by x. And that's the answer. If we had done it the long way, that's what we would have got. 207. The derivative with respect to x of this function here will be sine squared of e to the x. That's it. Sine squared e to the x, and then you're done. 208. The derivative with respect to x of this integral here will be e to the power 3x to the fifth minus pi squared. And then you're done. The derivative with respect to x of this will be square root of x. Okay. So all we're doing is we're replacing t by x or any letter that we have. But is it always going to be like this? And the answer is no. Okay. What if the upper limit or the lower limit are not x, they're different? Like 210. The upper limit in 210 is x to the fourth. This time, let's do it the long way first, and then we'll see what we're supposed to do. First, integrate. The integral of cosine t dt is sine t between the limits pi over 6 and x to the fourth. So this will be sine t, which is sine x to the fourth minus sine pi over 6. And then the derivative of this will be the derivative of sine x to the fourth. The derivative of sine pi over 6 is 0 because sine pi over 6 is a number. Use the chain rule. The derivative of sine is cosine x to the fourth times the derivative of x to the fourth, which is 4x cubed. Okay. So the rule, use any rule. Okay. Use the shortcut plus any rule, chain rule or any rule. We did not use the shortcut. We integrated, then we differentiated. So could we have used the shortcut? Let's use it here. Okay, the shortcut tells us to replace this t by this limit. So this answer here is going to be cosine the upper limit, which is x to the fourth. But this time it's not cosine x. The upper limit is not x, it's x to the fourth. So times the chain rule, the derivative of x to the fourth is 4x cubed. And that's what you do when one of these limits is not x. Now if the lower limit wasn't, then you do minus whatever it is and then use the chain rule with that also. Let's do another example. Shortcut, okay? 211. The derivative with respect to x over the integral of sine t dt from pi over 12 to x to the sixth will be directly, it'll be sine x to the sixth times 6x to the fifth. I'll write it in a minute. It's a sine x to the sixth times 6x to the fifth. I had cosine before because I was gonna do it the long way, but I didn't. So it'll be whatever this is, you replace this t by this limit, x to the sixth, times the derivative of x to the sixth, which is 6x to the fifth. In 212, we have e to the t, so it'll be, the answer is e to the power sine x times the derivative of sine x, which is cosine x. And that's using the second fundamental theorem of calculus. Next, we're going to go over some hyperbolic functions, the definitions. Hyperbolic functions are just functions that are combinations of e to the x and e to the minus x. The hyperbolic sine of x is e to the x minus e to the minus x over 2. And the hyperbolic cosine of x is e to the x plus e to the minus x over 2. The domain of both of these functions is all real numbers. That is from minus infinity to plus infinity. There are some good things about hyperbolic functions, and there's a lot of applications also in math, in science, in engineering, and so on. Let's find the derivative of hyperbolic sine of x. Its derivative, this is the hyperbolic sine, is e to the x minus e to the minus x over 2 prime. Take the 2 out, so it's 1/2, and the derivative of e to the x is itself, minus e to the minus x is itself, times the derivative of the exponent, which is -1. This negative and this negative will cancel, so that gives you plus 1/2 e to the x plus e to the minus x. But this is just the hyperbolic cosine. So the derivative of hyperbolic sine is hyperbolic cosine. Let's do the derivative of the hyperbolic cosine next. Okay. Here's the hyperbolic cosine. It's e to the x plus e to the minus x over 2 prime. Take the 2 out. The derivative of e to the x is e to the x plus e to the minus x times -1. Okay, I'm going to put this negative in front. So it'll be 1/2 e to the x minus e to the minus x. But this is just the hyperbolic sine. So the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of the hyperbolic cosine is the hyperbolic sine. Hyperbolic functions like cosine and sine are also easy to integrate. The integral of hyperbolic cosine is hyperbolic sine plus c. The integral of hyperbolic sine is hyperbolic cosine plus c. The good thing about this is you don't have to remember when to put a negative sign, not like trigonometric functions like cosine and sine. You need to remember, are you integrating or differentiating? Do I need to put a minus sign or not? With hyperbolic functions, we don't have that problem. The definition of hyperbolic tangent is hyperbolic sine over hyperbolic cosine, which is e to the x minus e to the minus x over e to the x plus e to the minus x. And the hyperbolic cotangent is hyperbolic cosine over hyperbolic sine, which is e to the x plus e to the minus x over e to the x minus e to the minus x. We're going to do an example of integration later on these functions. Okay, let us look at something we did before, but not quite like this. We did the use substitution before, integration by substitution, but there is a certain form of integrand if we come across, we don't even have to do the use substitution. For example, if you have a problem like 213, if you have x squared plus 10 down here and 2x up here, you could say let u equal x squared plus 10 and it works. So we could do this and go through the whole process of u substitution and it works. But you could also notice something else. If you notice that the form of the integrand is derivative divided by function, the result will always be a logarithm of the denominator. So it'll be ln of the absolute value of f of x. There is no dx, so I'll remove that dx. We've already integrated. Plus c. Okay. Let's apply it to 213. In 213, the integral of this is ln of x squared plus the x squared plus 10. Why? Because the derivative of the denominator x squared plus 10 is 2x. So you have derivative over function. So this will be ln of x squared plus 10 plus c. And then you're done. And you don't have to use the u substitution. Once you integrate, you don't need that dx like I had over there. So this is why I removed this. All right. 214, you have x cubed minus 1 down here. What's the derivative of x cubed? 3x squared. So you have derivative over function. Derivative over function. So the result will be ln of the denominator. Done. Plus c. This time I put absolute values around it because x cubed minus 1 could be negative. This one couldn't. Okay. What if you have something like this? What is the derivative of x to the fourth minus 6? Okay, I'll rewrite it. dx, okay. The derivative of x to the fourth minus 6 is 4x cubed, right? So this is missing a 4. We don't have a 4 on top. So what we do is we write a 4 on top, but we divide by 4. So it's 1/4 times the integral of 4x cubed over x to the fourth minus 6. That's it, and that's the trick. If you don't have the derivative exactly and it's only missing a number, you put that number and then you either divide or multiply to make the adjustments. 1/4 and 4 cancel each other out. So now look at this bracket here. Okay, the 1/4 is out. The bracket has derivative over function. So its integral will be the ln of x to the fourth minus 6 plus. So it's 1/4 ln of x to the fourth minus 6 plus c. Here's another one. You're integrating cosine hyperbolic x over sine hyperbolic x plus root 2. Well, the derivative of sine hyperbolic x plus root 2 is cosine hyperbolic x. So we have derivative over function. So the result will be ln of the denominator plus c. One more example. The integral of tangent hyperbolic x dx. Tangent hyperbolic x is sine hyperbolic over cosine hyperbolic. So if you look at cosine hyperbolic, its derivative is sine hyperbolic. So you have derivative over function. Therefore, this integral here will be ln of the denominator. And you could put this in parentheses or in absolute values. Plus c.